What's up, guys? I'm Chad Barnes, and welcome to the channel. Here, it's all about real car talk, from simple fixes to smart driving tips and keeping your ride in top shape. If that sounds good to you, go ahead and give the video a thumbs up. Hit that subscribe button and make sure you watch all the way through. There's a lot of good stuff coming. Let's get to it.
Designs of electric actuators of automobile exterior rearview mirrors. There are quite a lot, although the differences between them are not too fundamental. In any variant, the drive is a sealed case with two miniature electric motors. Two extending rods come out of it, which tilt on two axes, horizontal and vertical, oscillating on the central axis of the movable panel dash plate. A mirror element is attached to the plate. The kinematics of the actuators may differ slightly from manufacturer to manufacturer and even be protected by patents, but inside any variant there is a mechanism that turns radial rotation of the electric motor shaft into linear motion of the rod, changing the angle of inclination of the mirror. Actually, such mechanisms are called linear drives. Any modern car is full of them. They include seat movement, trunk lift, headlight corrector, idle speed adjustment, and much more. Electric motors in mirrors are the simplest, typical motors of standardized sizes. They can be found anywhere, including in children's toys. They are primitive collector motors, often without full bearings and usually without even graphite brushes. The brushes are spring-loaded metal plates. The motors are controlled by a simple voltage supply with polarity reversal, which makes them change the direction of rotation and, accordingly, the direction of linear movement of the rod, inward or outward. In mirrors with the function of position memory, there are also variable resistors installed next to the motors, the sliding contacts, of which are mechanically connected with the moving rods of the mechanisms. Accordingly, the resistance of the two resistors changes with the movement of the mirror. The electronic unit, located in the passenger compartment, memorizes the resistance value in the mirror position you have chosen and, when automatically setting the mirror position, simply turns the motors until it is reached. This is how the mirrors of 99% of cars, from budget to premium, are set up. Once you've seen the guts of one of them, you've seen them all. What is the transmission of the mirror drive? As we have already mentioned, mirrors use varieties of linear drive, which allow to convert the rotation of the electric motor into reciprocating motion and at the same time significantly increase the torque, because it is insignificant on the shaft of the miniature motor and it is not enough for the mirror movement. In the transmission can be used worm gear or spur gears. It happens in different ways, although the essence of this does not change. In the actuator, which we took apart for the article, is a worm, and directly linear motion is created by a movable threaded rod moving in a fixed rotating nut. How reliable are the mechanics of such actuators? Very reliable, and by itself it can work for almost decades. If we take the drive of a good brand, or even more so, under the original marking of the car manufacturer, it has gears and rods made of very high-quality plastic, with a negligible coefficient of friction, retaining strength in a wide range of temperatures and not acquiring brittleness over the years, grease embedded in the mechanism, which does not lose its plasticity at all temperatures, and does not tend to thicken over time, structurally ensured backlashes in the mechanism, which are compensated for by elastic elements, but do not allow the mechanism to lock up if it is left idle for any length of time. Is it dangerous to operate the actuator mechanism up to the stop? As a rule, no. The above-mentioned design backlashes are simple, yet very clever solutions. Take, for example, a threaded rod moving linearly in a rotating, stationary nut. There is, of course, no nut in the conventional sense. It is a number of elastic lobes with teeth entering the threads of the rod. Where a nut of the traditional design, having been bumped, spoils the threads in itself or on the screw, the pedal nut jumps over the threads, only slightly snapping. No, of course, if you will be beating an hour to hold the adjustment button of the mirror, which has reached the extreme position, it is likely that something in the mechanism of the transmission of the drive will rub off or destroy. But, agree, these are still extremes. As they say, give a fool a glass ball, he will break the ball and cut his hands. Is it dangerous for the drive mechanism to work when the mirror element freezes in the casing? Again, no. The effect is similar to the aforementioned pushing all the way to the stop. The mechanism will click, and it will be protected from breakage and wear by slippage of elastic elements and lubrication. Although, of course, it is not necessary to press the joystick for a long time, hearing the clicks and not seeing the result. Is reverse movement dangerous? When not the electric drive moves the mirror element, but we swing the mirror with our hands, forcing the mechanism to move from the opposite side? And this is what the manufacturer provides for. Despite the fact that such a process is not really a norm, forced manual movement of the electric mirror when wiping it after washing, or in order to break the ice interfering with the movement, is possible in everyday use of the car. If you don't do it intentionally, regularly, and daily, the mechanism's safety margin and its foolproofing will last for a long time. So what is the main danger for the mechanism of electric mirror adjustment, if it is supposedly so reliable and durable? The most ordinary water. Whatever the design of the transmission inside the actuator housing, there are two moving elements, rod or lever, depending on how the particular manufacturer implemented it. And the exit points of these moving elements represent a potential entry point for moisture inside the motor housings and resistors, with some associated electronics in the memory mirror versions. As a rule, the output of the rods is very well protected by complex profile corrugated rubber dust covers, similar to the dust covers of brake bracket fingers, and as long as they have not lost their integrity, elasticity, their protection successfully resists even a jet of water from a Kircher beating directly under the mirror element, including for a long time, not just in passing. However, the rubber dust cover is still the most vulnerable element in the design of the electric mirror drive. Over time, it loses its qualities and becomes covered with small cracks. After that, it starts to tear from the same water jet at the car wash, and from the frozen ice, if we adjust the mirror in severe frost. When the dust cover is torn, moisture and dust are drawn inside the mechanism. It rots the brushes on the motors, thickens the grease in the gears, damages the feedback resistors for the memory function. The mechanism begins to work slowly, with stuttering, and then fails altogether. Although repairing it is possible, it is cost-effective only in rare cases, unless you have similar donor mechanisms from which you can rearrange individual parts. In conclusion, the mirror drive represents a fascinating intersection of engineering and nature, showcasing how gears, frost, and water can work together in a delicate balance. While its design is robust and innovative, understanding its vulnerabilities is equally important. Whether it can withstand extreme conditions or face potential breakdowns depends on various factors, including maintenance and environmental influences. As we continue to explore and refine this technology, the mirror drive stands as a testament to human ingenuity and the challenges we face in pushing the boundaries of what is possible. Thank you for joining us on this journey into the mechanics of the mirror drive.